When we have a phase change, we have to consider the fact that the internal energy of the system is not just due to the kinetic energy anymore. We also have bonds that are forming, and therefore internal energy also depends on the potential energy and the different interactions that molecules will have, van der Waals forces, will lead to potential energy. So in this section, we're going to look at, we'll probably look at more in terms of a conceptual approach. We're going to look at real gases, okay? A real gas does have interactions between molecules, can change phase, unlike an ideal gas, which the ideal gas is an approximation where the gas molecules have no volume, they don't interact with one another. Let's see what happens when we deal with real gases and phase changes. Now, if I graph pressure as a function of volume, and I look at the phase diagram of this now, I notice that where before everything was a gas, now I have to worry about different regions that have different phases. Like over here, we have solids. Actually, if you take a look at this right here, we have solid right here. Over to the left, we have solid and liquid phase together. Okay, over here, we have all liquid. Okay, over here, we have all vapor or all gas. And in between them, we have both liquid phase and gas phase. Okay, now what we've looked at before, we've talked about the work being done equal to the integral of P dV, okay? Basically saying, look at the area underneath the graph, and that will be equal to look at the area underneath the graph, that'll be equal to the work. Now, for a real gas, the isotherms are no longer these 1/x lines, up at higher temperatures, a gas, still acts very much like an ideal gas. But as we get closer and closer to phase change, look what happens. Notice that we start getting these kinks in the line. And then finally, when a phase change takes place, we know that a phase change indicates no change in temperature. So when we're crossing through a region with more than one phase, it will actually go horizontal. And then you can see the isotherm going off in that direction right there. So, it creates a little bit of a challenge in terms of the complexity of the system. But in some cases, calculating the work done actually becomes a little bit easier, and we'll see why in a second. Now, once again, here's our equation for the first law of thermodynamics, which talks about the change in internal energy being equal to the heat added to the system minus the work done by the system. Okay, so the first law of thermodynamics is still going to apply in this particular case. But the problem here is heat added to the system is also going to lead to phase changes. Okay, and whereas with an ideal gas, it just simply expands as we increase the temperature. Here we can actually have an even more rapid expansion, not so much due to a temperature change, but rather a phase change. What do I mean by that? Well, think about this. Generally, a liquid tends to be somewhere around 1,000 times more dense than a gas. So when I undergo a phase change, let's say I go from the liquid phase to the gaseous phase, okay? If it's water turning into steam, you can talk about a factor of 3 magnitudes change in volume, okay? So once again, In the past, we've basically said, well, Q equals mc delta T when we have a temperature change. For the molar heat capacity, it becomes NC, constant pressure, P delta T. Okay, but now the heat is going simply into breaking bonds or changing the van der Waals forces, and that's leading to a rapid increase in volume. Okay, so let's take a look at a phase change. This would probably be a pretty good representation of steam boiling. So we're over here on the left-hand side. We are in the liquid phase, okay? All 100% liquid, okay? But as we go into this green area, we have both a liquid and a vapor, okay? So basically, on this side, okay, the left-hand side of the curve, we would be 100% liquid, and on the right-hand side of the curve, we'd be 100% vapor. So we can imagine allowing a water to boil, go from the liquid phase to the vapor phase, or cross through a turbine going from the liquid phase to the vapor phase. And we can see here, going from this point to this point, let me change colors, that's a little hard to see, from the initial to the final, that as it expanded, okay, it went from 100% liquid to 100% vapor. There'd be quite a bit of area underneath here. So that work would be equal to pressure times a change in volume. Okay. Again, as long as it's expanding at a constant pressure, calculating the work would be pretty much straightforward right there. So, but in any case, again, it gets a little more complicated when we do have a phase change. We have to look at what the pressure is as a function of volume and integrate underneath there. If we're expanding at constant temperature, which most phase changes take place, usually it becomes pretty easy to calculate or at least approximate what that work is there. Okay. So it's a little bit different from the ideal gas, where we have very well-defined quasi-static processes. And again, this is very, very important for when we talk about things like a steam engine and the Rankine process, which is used to generate work from the expansion of steam. Just a quick summary for ideal gases, or when we approximate things as an ideal gas. Isobaric is the case where we can just calculate the work done simply by taking the pressure times the change in volume. Isovolumetric, there is no change in volume, so no work is done. So that's a really easy one to do. Okay. Isothermal, for an isothermal process, as shown in C, we follow a isotherm in terms of pressure versus volume. When we did the calculation for work there, it's a little more complicated. The pressure is inversely proportional to the volume for an ideal gas. So we've got nRT, natural log, final volume divided by initial volume. Okay, and that's the work done for an isothermal. Adiabatic, as long as we can calculate what the internal energy of the system, we can say that the work done is equal to the negative change in the internal energy. Okay, that's that green right there. We're following an adiabat. And of course, our change in internal energy for an ideal gas depends on the number of moles, the molar specific heat, and also the change in temperature. So we're going to put these four processes together to create one complete cycle. Okay. Again, isobaric, isochoric or isovolumetric. Isobaric is a horizontal line, work equals P delta V. Isochoric is a vertical line. Here, work is equal to 0. Okay. There's a change in internal energy because we're changing the temperature. The change in internal energy is N CV delta T, but no work is done. Isothermal, as we said, work is equal to nRT times the natural log of V final over V initial. Here, all the heat that's added into the system is converted to work. And then finally, adiabatic, where delta U is equal to the negative W, or the work is equal to the negative change in the internal energy. First law of thermodynamics simply states that the change in internal energy is equal to how much heat we add to the system minus how much work it does. And finally, we will calculate the work done during a single cyclical process. We can imagine we can put a few of these quasi-static processes together and go from some initial point all the way around some path. And the area enclosed by the path, okay, we'll say that this point A represents our initial and final point. The area enclosed in here is equal to the work done during an entire cycle. So for instance, we could imagine that, let's say I put a few of these processes together, okay? I start out, first of all, with, what should I start with? Let's start out with, first of all, at this point right here. Let's say I have an isobaric expansion, okay? I go from point A to point B, okay? I know that doesn't look like a perfect horizontal line, but I did the best that I could. Let's say that next I follow that with an isochoric process. I simply cool down the gas. I go down to C. Then I follow, let's say, an isothermal process. I go to this point right here. I'll call that D. And then I can have an adiabatic process on top of that from D back to A. Okay. So isobaric, isochoric, isothermal, adiabatic. That could be a process that a cylinder, or I should say a piston in a cylinder, well, cylinder undergoes. To calculate the work, it would just be whatever's enclosed in all these processes. But in the next chapter, we are going to calculate the total work done by a cyclical process that involves a few different thermodynamic processes put together. Okay?